Thanks very much. So today I'll be talking about a dynamic lithosphere-asthenosphere boundary. And before I begin, I'd just like to thank an excellent team of collaborators whose work I'll show today. So the notion of a rigid lithosphere that transfers to a weaker asthenosphere is a widely accepted aspect of plate tectonic theory. However, the exact depth of that transition and also the mechanism that defines the lithosphere-asthenosphere boundary is not precisely known, and it's also widely debated. However, there are really important implications of our understanding of the lithosphere-asthenosphere boundary, or LAB. So for instance, it affects our understanding of the driving forces of the plates. So if the LAB is quite gradual, you might expect that the layers are relatively coupled and that ridge push from below might play a larger role in driving the system. Whereas if the boundary is quite sharp, you might expect that the layers are relatively decoupled and that slab pull plays a larger role in driving the system. And of course, this is very important to our understanding of many things that impact our life on the planet. For instance, the fact that plate tectonics causes many natural disasters like earthquakes and volcanoes, and it also influences our understanding of climate change over geologic timescales. So we'd like to know more. So the classic definition of the LAB is that it is determined thermally. And the ocean lithosphere is probably the ideal place to consider the LAB in its thermal definition because it has a relatively simple and short history. And we can take the predicted temperatures and translate them to seismic velocity, and we have a pretty good idea of what those would look like. You can see for a range of seafloor ages, we have a predicted gradual transition from the lithosphere to the asthenosphere for a thermal model. And on the left, I've plotted up a compilation of observations from scattered waves across the oceans. And you can see that looking at normal lithosphere on the top, we're doing a pretty good job. They seem to be pulling out a single kind of depth of thickness of the plate. It gets thicker with age, as we expect. There's some scatter, but it also falls along these viscosity contours in the back, where viscosity is really starting to decrease rapidly, predicted viscosity. So that's great. However, the fact that they're scatter, and also when we consider the fact that when you consider all oceanic lithosphere, including things by hotspots, say, or previously affected by hotspots, you get much more scatter. What this suggests is that overall, there is thickening with age, and therefore temperature plays an important role in determining the depth of the LAB. However, the fact that all of these scattered wave observations require something sharper, something more like this, in terms of a velocity gradient in depth, and also all of this scatter suggests that something else is going on, and there's more to it than just a purely thermal model. And this is not just true from scattered wave perspective. When we consider things like surface waves, it's well known that surface waves frequently image very strong velocity anomalies that are too slow to be explained by a purely thermal model. And this is also true for electromagnetics. So there's also very strong conductivity anomalies that can't be explained thermally. So a wide variety of subsolidus possibilities have been suggested. Things like a change in radial anisotropy or azimuthal anisotropy with depth, the oxidation state of the mantle. We could have a mechanism like elastically accommodated ground boundary sliding, or near solidus conditions. While these have been developed to explain a set of the observations I just described, it's actually very difficult for any one of these to explain all of the observations from a wide range of sensitivities and resolutions, including things like seismic waves and magnetotellurics. So the easiest thing to explain a wide variety of sensitivities is probably partial melt, given that it affects seismic waves and electrical resistivity, et cetera. If melt exists in the mantle, it likely decreases the viscosity of the mantle, and therefore impacts mantle dynamics. So we'd like to know more about that melt. However, melt has been proposed in a wide variety of scenarios in the mantle. It's been suggested that melt exists in a very thin channel at the base of the plate, perhaps ponding along the base of a permeability boundary. It may exist in a more complex matrix beneath the ridge. It could exist in this wide melt triangle beneath the ridge, so something more like this, or it could exist in a very, very narrow melt column, something like this. And the way it falls off with depth could also be variable. It could be very gradual, as implied by this 1D velocity profile, or it could be quite abrupt, as suggested by these receiver function results. So we'd like to know a lot more about where and how much melt exists. So to consider this in greater detail, we designed an experiment to look at a ridge from 0 to 80 million year old lithosphere at the slow spreading mid-Atlantic ridge using a range of resolutions and sensitivities all in one location. We deployed 39 ocean bottom seismometers and 39 ocean bottom magnetotelluric instruments, collected a host of marine geophysics data, and there's also an active source component. And this is the PyLab experiment. It also involves Eurolab, CALab, and Transatlantic iLab. So first of all, we have the Rayleigh wave results. You can see, first of all, at 26 kilometers depth, we find slow velocities beneath the ridge. So that's good. And we get faster velocities at older ages. That's what we expect. When we move to deeper depths, say here 78 kilometers, we lose all expression of the plate, and instead we see punctuated anomalies that are not necessarily centered beneath the ridge axes. Same story is true in cross section. You can see that the lithosphere gets thicker and seismically faster with age. This is true both in the north and in the south. And then at depth, we have these punctuated anomalies that are not really necessarily beneath the ridge. We also see evidence for a fast seismic velocity anomaly, possibly a downwelling. So the receiver functions in the south find a beautiful moho. We see an LAB phase that's just beautiful. It migrates to about 30 kilometers beneath the ridge and gets a bit deeper down to about 80 kilometers beneath 30 million year old seafloor. That's really, really nice. But we also have some complications and it's not so beautiful everywhere. That's good, it's science, that's necessary, right? So on the right, we have a more patchy LAB. We found a little anomaly here. You notice that it's right above the place where we have the surface wave anomaly. So that's promising, the fact that you have some agreement between where the strongest or the slowest velocities are in the asthenosphere and where we see this phase. It's much weaker and not visible on either side. The other really amazing thing is that this phase agrees really well with active source results. They find a really strong reflector right here. What that suggests is that thing is really sharp. I mean, we can say it's something like less than 30 kilometers in depth, occurring over less than 30 kilometers. Active source means, if you see it in active source, it really means it's occurring over less than 1 kilometer. So that's really, really interesting. In the north, we have more complications. We see kind of some kind of phase approaching approaching the ridge in the south and the north in the western side, but in the east it's more undulating, and a lot of these parts of the phase are not very well resolved, perhaps because there's topography on them, and so it's because of the lateral variability we're going to get too much variation in the waveforms. So now we're going to bring it all together, and now in the background I have the magnetotelluric anomalies. Surface waves are contoured in black, and the receiver functions are shown in purple. And what we see first is we see a beautiful thin channel from the magnetotellurics in the southeast. That's really impressive. We were wondering whether we'd see a channel at all, and we see it. It is not very well resolved with the seismics, and that's probably because seismic waves have trouble resolving things that are very thin, like say on the order of 10 kilometers, because of waveform interference. We see this kind of one patch in the surface waves and the receiver functions where there's probably a bit of a thicker amount of melt beneath the plate. In the southwest, we see the receiver functions getting thicker with age, and that's in pretty good agreement with the surface waves and the MT. There's probably there's thicker layer of melt, the gradual drop off with depth. In the north, we see these punctuated anomalies. There's pretty good agreement between surface waves and MT, but we don't see any clear things at the base of the plate, more undulating things like one anomaly here, one anomaly here, a fast anomaly here. We see, of course, the receiver function getting really strong above that really slow velocity anomaly. But it's really not anything like the character of what we see in the south.
10 minutes over.
Okay, 10 minutes. Okay, good. Okay, so what's really nice about the punctuated anomalies is these things have been predicted by geodynamic models. The fact that you might have some active upwelling and some small scale convection, and that might bring temperatures, hotter temperatures shallow, and then also cause a small amount of decompression melting. So that's really nice. Overall, we have a model in which we have these ascending melt anomalies that seem to be feeding melt channels beneath the plate. The channels are sometimes thicker and sometimes very thin. And then in some cases, it doesn't seem like there is any kind of channel at all, more melt channels affecting the base of the plate and causing these undulating features. If the melt exists, it's going to decrease the viscosity of the mantle and define the plate. And that suggests that the LAB is determined by melt generation and migration. It's dynamic and it's laterally variable, and also in time. So what this really does is it reconciles all of these reports of melt in a variety of ways. The idea that you have these wide melt triangles, very thin ones, punctuated anomalies, melt in channels, or ponded beneath a permeability boundary. These are not necessarily an artifact of resolution because we've seen them melt in many ways in our one study area. It suggests that all of these can be true, just that the melt is changing the way it exists in the mantle over time. This has also been, this is also true when we compile looking at the way melt has been interpreted beneath the plate as it subducts as well. Beneath very old lithosphere, it could exist in very thin channels or in larger blobs. So that may also be true. And now bringing this to rifts, I just want to point out this really nice work from Emma Chambers, where she did Rayleigh wave tomography beneath the FAR. And you can see that she sees these beautiful punctuated anomalies, very similar to what we're seeing in the Atlantic. And that's all the way through the rift region here, say at about 100 kilometers depth. Whereas at shallower depths in the crust, she sees really strong anomalies that she thinks are melting, but they're not necessarily associated with any deeper anomaly. What this means is that either melt is ephemeral, it existed in the past in the mantle and is now beneath the crust and now is in the mantle, but is not in the crust yet, or it suggests that melt is migrating laterally. Either way, it's dynamic, much more dynamic than most models of melting. And how does this fit in with our global understanding? Globally, we have these very smooth ideas for what the plate looks like, and as you can see, there's very clear tectonic variations. That means that temperature is important to first order. However, when we consider you have the averages here as the colored lines, compared to a bunch of observations that are pretty discrepant on top of that, but the discrepancies could be real and related to resolution if all of the background lines, which are the gray lines, are actually true, that there's so much variability within any given tectonic region or within any given craton. And so when we consider our very smooth typical model of the oceans in large age bins, when we average surface waves, you see there's this very smooth monotonic lithosphere that we typically think is true. Whereas if you look at a single transect, you see that you get much more punctuated anomalies. Whether or not that was related to resolution or not is not really known, but our study suggests that it's much more likely a real features. This is also true when we look at the continents. Surface waves give us a very smooth image of the continent, whereas the geochemical viewpoint is that you have a much more corrugated base to the continent. And this really reconciles a host of observations from receiver functions that both see and don't see discontinuities in comparison to SS waves, which would have a large lateral sensitivity. So would see this as a single discontinuity. It also reconciles this kind of long-held discrepancy between scatter waves, which find things at like around 150 kilometers beneath continents, in comparison to these deep 250-kilometer phenomena from temperature and also surface waves. But when we now analyze this further, we found that these very deep areas only persisted over somewhere between 6 and 14% of continental interiors. It suggests a picture like what we just saw there is much more likely the case. So this is kind of the summary figure where you kind of have melt rising. It may affect the thickness of the lithosphere, and you also may have these downwellings and kind of ponded melt in areas of neutral buoyancy. And this is really consistent with some really nice two-phase flow geodynamic modeling, where they're getting these also ephemeral melt phenomena, where the melt rises, it sometimes feeds these channels. The channels get thicker and more concentrated in melt, and then eventually the melt leaves. And so it's really good to have that agreement. Some nice work that we've been doing recently is just taking those geodynamic models, translating them to velocity, and then seeing what we would resolve with surface waves and receiver functions. And that's it. I mean, overall, the LAB is increasing with age, but it's not always monotonic. There is evidence for active upwelling. This could be a good mechanism for plate flattening. We find punctuated melt anomalies, channels of variable thickness, and the melt itself is probably ephemeral. It suggests that the LAB is dynamic and determined by melt generation and migration. And this melt may also aid buoyancy and help plate tectonics. The channels themselves may weaken the mantle and also facilitate the motion of the lithosphere over the asthenosphere. Thank you.
Excellent. Thanks a lot. We have time for probably one question. If anybody is quick, you can just raise your hand or unmute and ask. Otherwise, I would have a question. You chose the area to be in a highly oblique mid-ocean ridge setting where you have many transform faults. So I was wondering about the effect of these transform faults and the fracture zones on the along strike variability. What did you find out?
Yeah, I mean, I think, okay, so that's a really good point. We chose this area. There's a lot of reasons that went into choosing this. We wanted a very long segment because of the surface wave resolution. And then we also wanted to be coincident with the active source experiment. And then they had trouble with territorial water rights because they're using an industry ship. So there was so many factors in the decision of where to go. And where we ended up going, I think worked out great because we have some great results. But some of the small scale convection that we're seeing, you're right, could be directly related to those large offset transforms. I mean, we predict that you'd get these kinds of things happening near the long offset transforms. So I just suggest that if we want to know exactly how everything works, that we look at other sections of the ridge.
Okay, excellent. Thanks a lot. We are close to 18 minutes now, so if people are typing their questions, then maybe you can answer them in the chat. And otherwise, thanks for that great talk.
Thank you.